So the next talk will be given by Dorsa Sadigh from Stanford University, and she's going to talk to us about mixed autonomy.
All right, so hi everyone. Thanks for inviting me, and thanks for the introduction. So I'm Dorsa, and my research is in learning and control for human-robot systems. So today I want to talk about a specific type of interaction that we have in human-robot systems, and that is specifically influencing interactions. So interactions that influence people, okay? So when we think about interaction, the first thing that we might remember is human-human interaction. Humans are really good at this. They easily come into each other's spaces, they collaborate with each other, coordinate with each other, and do very complex manipulations tasks. But one thing that humans are really amazing at, and every time I look at it, I'm just like really amazed by how people do it, is influencing interactions. People tend to take actions that actually influence other humans around them and influence the decisions of other humans and what they're going to do next. And we do see this in like tricking people or manipulating people. We see this in games. We see this in sports. We see this in stock market. In general, like this comes up all the time. And another place, for example, that we see influencing interactions is in driving. So for example, if you have a car that wants to change lanes, what it does is it starts nudging in front of other drivers, and it makes them slow down to make room for them. So it doesn't assume other drivers are just moving an obstacle, or just a moving obstacle, because if it assumes that, it can't really change lanes. It doesn't just cut in front of people either, because it thinks about how it can influence other drivers to slow down and make room for it. So ideally, what I would want to have is I would want to have robots that can influence people. Okay, so that would be the ideal case. And why do I want to do that? Because if I don't have robots that influence people, I end up in scenarios that kind of look like this. So this is a video of a Waymo car that is trying to change lanes. It's in an exit lane. It starts signaling, so it actually starts trying to influence people, but it is not able to use motion to coordinate with other drivers. It's not trying to interact with other drivers around, so because of that, it is actually not able to do this change lane behavior, and it has to exit and come back around and try this again. So that is not ideal, right? Ideally, I would want to be able to plan for my robots so they can influence people, and they can influence them positively, so we have a better outcome of the overall system. That is my big goal. And I would want to see that in many different settings. And we've been looking at this idea of influencing interactions in a variety of applications. We've been looking at autonomous driving, robotics, manipulation. More recently, we have been thinking about human-robot teaming. And language is also some other area that I'm super excited about, and how influencing comes up there. But the specific thing I would want to talk about today is about mixed autonomy traffic. So we can also see influencing interactions and influencing behaviors when we have multiple autonomous cars and human-driven cars interacting with each other. And this is joint work with Ramtin Padarsani at UC Santa Barbara and our students Erdem and Daniel. Okay? So let me focus on that, and then at the end, I'll come back to this slide, and I'll talk about some of the other exciting areas that I think it would be cool to think about influencing behaviors and some of the future directions of that. Okay? So let's talk about traffic. Okay? So traffic is an important problem. It's an expensive problem. It's becoming more and more expensive every year. This is a video of traffic in the LA area on an afternoon before Thanksgiving. This video stresses me out, so I'm not going to look at it for too long. But I don't think I need to convince you guys that traffic is a difficult problem, or it's an important problem. And people have been looking at traffic for a long time, right? People have been thinking about building roads, decreasing demands. There are many other ways of thinking about helping with traffic. And what we think is we think we can use autonomous vehicles to actually help this congestion problem, this existing traffic problems. So I started working on autonomous driving beginning of my PhD in 2012, and at the time, car companies were telling us that we were going to have autonomous cars by 2020. Well, that is next year. I'm kind of excited about that. I don't know if I should believe them, but if you're going to have autonomous cars by 2020, or at some point in the future, I think we can benefit from them when we think about some of these global objectives or societal scale objectives that we would care about, for example, traffic. Okay? So of course, we are not the first people who have thought about this. So people have been thinking about this idea of using autonomous cars or connected vehicles in various setups. So car platooning and truck platooning was an idea that started from the Berkeley Path project, where you have vehicles, connected vehicles that have a small headway between them. And using that, you can actually increase the capacity of the road, and you can help with traffic. There are people in this room who has worked on mixed autonomy traffic a lot. So Alex Bannon's group, Kathy Wu, Saurabh Amin, Sam Coogan. There are a lot of different people who have been thinking about this problem. Some of the more recent work is some of the stuff that Kathy talked about yesterday, so thinking about smoothing instabilities. And also, more recently, people have been thinking about ride sharing and mobility on demand and how we can go about that. So the way that we think about this problem is, can we use autonomous cars, can we leverage autonomous cars to influence the routing decisions of human-driven cars, and based on that, try to reduce congestion? So the problem we are looking at is a routing problem. It's a routing game problem. Okay? So I have a traffic network with n parallel roads. I can have autonomous cars, and I can have human-driven cars. The human-driven cars in this case are selfish, so they're going to decide based on minimizing their own delay. But the autonomous cars, we've assumed various setups. We've assumed cases where autonomous cars are also selfish. We've also assumed cases where autonomous cars can be altruistic, where altruism in this case means that autonomous cars are willing to take just a little bit longer than human-driven cars. And also, we have considered cases where we can fully control the autonomous cars. There would be a social planner that tells what the autonomous cars would do. Okay? So under this traffic network, the problem that I'm very interested in is this dynamic routing problem. So dynamically, how can I route my autonomous cars in order to influence the routing decisions of human-driven cars? And through that, how can I reduce congestion? That would be really cool, right? If we were able to route autonomous cars in a way that helps traffic, that would be really cool. But I guess a question that we can ask before this is a static problem. It's a game theoretic version of this problem. So what I mean by that is, it would be cool to reduce congestion, but maybe another question that we can ask is, if I just have a mixed autonomy traffic network, if I have a bunch of autonomous cars and human-driven cars, what are some behaviors that emerge? Like, what are some equilibria? Like, can we at least even characterize what are some equilibria that we care about, so then when we think about the dynamic problem, we can actually work towards something, work towards those equilibria that we really like. So I'm going to first talking about the static problem, characterizing these equilibria, and then after that, I'm going to switch to the dynamic routing problem and how we go about solving it. Okay, so that's our plan. All right, so let's talk about the static problem. So to talk about equilibria, we need to have a model of traffic. And the way we model traffic is by using this idea of the fundamental diagram of traffic. A lot of you might have seen this, but let me just go over it. So the idea is, I want to have a representation that relates flow and density. So when I put more cars on this road, then the flow is going to go up. So if I start putting more cars, we increase density, the flow of the road is going to go up. And that is when we are in a free flow regime. So we add cars are just going, everything is great. But at some point, we get to a point which is called the critical density, which is where we are starting to get congestion. And then after that point, if I start adding more and more cars, then actually the flow starts going down. And that is when we are in this congested regime, where we have congestion. And when this line hits the x-axis, that is when we are at the jam density. So the traffic, we have traffic jam. Another view of this fundamental diagram of traffic is to thinking about latency versus flow. So when we are in free flow, we can assume that we have constant latency. So everyone has the same latency. And again, at some point, we get to the critical density. And then after that, we're going to get congestion, so the latency is going to go up. So these two diagrams, you can use them interchangeably. And every time I talk about the road, I can represent that road using one of these diagrams. So that is the tool that I'm going to use. Okay? So when we have autonomous cars, what we're going to do is we're going to extend this diagram to think about what would be the effect of the autonomous cars. So when we have autonomous cars can platoon in the best case scenario, but can also in general increase the capacity of the road. And because they can increase the capacity of the road, that is going to push the critical density a little bit to the right. So what's going to happen is, if I have autonomous cars, the critical density is going to be pushed a little bit to the right, and I can actually have a higher density in free flow regime. And similarly, in the other plot, the critical density is going to be pushed to the right. The way we model this is by having this notion of critical density as a function of autonomy level. So alpha is the fraction of autonomous cars that I'm going to have on a road. So that's my autonomy level. And it's going to be inversely related to the average headway plus the length of a car, where average headway is dependent on the short headway and long headway, short headway for the autonomous cars, long headway for the human-driven cars. Okay, so this is my model. So let's go back to the question that I'm interested in. So what I want to do is, based on that model, I want to be able to think about equilibria. So what are some equilibria that we would get when we have this mixed autonomy road. So let's characterize what is even an equilibria. So we're defining an equilibria to be a situation where no selfish user has any incentives to unilaterally deviate from their current strategy. So let me show an example. So let's say we are in a setting where we are in LA. So we have 3 roads. We have the 405, we have Coldwater, and Laurel is this canyon road on the side. Okay? And I'm going to have these 3 roads, so I can represent them using the latency flow fundamental diagram of traffic. So I have 3 roads. Notice that Laurel has the higher latency than everything else. And I'm going to put cars on this road. So the cars are going to take Coldwater, right, because that's the shorter road. So they're going to be in the, one possible equilibria is they're going to be in the congested regime on Coldwater, and a bunch of other cars are going to go on 405, and they're going to be in the free flow regime in 405. So that is one possible equilibria. So actually, there is work from Alex Payne and Saurabh Amin's groups where they have looked at this problem, and they've shown that if we have one type of vehicle, there's a finite number of equilibria that we can have. So what we are looking at is what if we have mixed autonomy? What if we have 2 types of vehicles? And what we have shown is that if we have 2 types of vehicles, we actually have an infinite number of equilibria. So I'm just going to show this quickly through an example so you get an idea of why we have a continuum of equilibria. So what is going to happen is, imagine, OK, you'll have the same roads. I'm going to consider 2 roads instead of 3 roads to make my life easier. So let's say I have these 2 roads. If I have autonomous cars, these plots are going to change. So they're going to be extended depending on the autonomy level. And one equilibrium is when I put all the human-driven cars on 405, and autonomous cars are going to be split between 405 and Coldwater. Another possible equilibrium is going to be the other extreme when I'm putting all the human-driven cars on Coldwater, and all the autonomous cars are going to be on 405. And anything in between these 2, like any combination of these 2, is also going to be an equilibria, and that's why we have a continuum of equilibria. So because we have a continuum of equilibria, then the best equilibria we are looking for, which is the thing that has the lowest latency, is not unique anymore. And the question is, what is a better equilibria? If I have a bunch of different equilibria in this case, which one would I prefer? So we characterize that through this notion of robustness. And we define robustness as a thing that quantifies how much extra unexpected flow demand can be handled without disturbing the equilibrium. So we characterize the fact that, well, I have different type of equilibria here. All of them have the same latency, but one is going to be more robust than the other. So one is going to be able to handle more traffic if I add more traffic. Okay? So we call that the robust best Nash equilibria. And in addition to that, we have been looking at a set of properties of these different Nash equilibria that we can get. So specifically, we have been looking at properties of best Nash equilibria. And we have proved some of these properties, but I'm just going to go over them. If you're interested in them, I can talk about them offline. So one property is there's exactly one road that will be in free flow. Okay? And in addition to that, all roads with lower free flow latency will be congested. And all roads with higher free flow latency will have no flow on them. Okay? So these are properties that you can actually show when we have this mixed autonomy traffic and when we are looking at best Nash equilibria. And the reason I'm defining these properties and I'm proving these properties is I can use these properties to compute my equilibria. So remember, my biggest goal here in the static case was, what are the equilibria? Can I compute them? How do I go about computing them? And I've defined a fundamental diagram of traffic to talk about them. I've defined these properties. And the reason I've talked about these properties is I want to use them in order to compute what these equilibria are. Okay? So the way we can compute these equilibria is we can have this naive approach where we think of it as a search problem, where the search space is all possible latencies and the routings that yield them. And if I think about it that way, then I have a combinatorial problem. It's a non-convex combinatorial optimization. I don't have any hope. But if I use the properties that we have shown, like those properties that the fact that there's exactly one road at free flow, then we can actually reduce the search space much more. And we end up with a polynomial time algorithm that tries to find these equilibria. So what we exactly have is we have a polynomial time algorithm that allows us to find the robust best Nash equilibria in the order of n to the 4, where n is the number of roads. And the way we find these equilibria is, again, through an optimization. So what we do is I want to find my equilibria. I want to minimize my total delay subject to a set of constraints like flow conservation, non-negative flows, road capacity, and the fact that I need to be at equilibrium. And this particular constraint, the constraint that is about equilibrium, I can replace that with a much simpler constraint based on the fact that I have these properties. And then this ends up becoming a linear program. I can solve it using my polynomial time algorithm. All right, so let's look at how these equilibria actually look like. So in the first case, I have one Nash equilibrium. It's actually a congested Nash equilibrium. These are 4 roads. These are not lanes. They're kind of like stuck together. But these are basically those 4 roads that we have right there. They're different length. It's hard to visualize these things. So they're different length, but they're 4 roads running at autonomy level of 0.75. And you can see the latency on the side. So this is one Nash equilibria that one can get in mixed autonomy. What we look at is we look at the robust best Nash equilibrium. The robust best Nash equilibrium is going to have lower latency. Notice that one of the roads is not even being used because we don't need to use it. And then we also look at altruism. I didn't go over that much, but in the case of altruism, in this case, I'm assuming my autonomous cars are willing to take 1.5 times longer than human-driven cars. So under that scenario, I have this best altruistic Nash equilibrium, where I can bring down the total latency of all the roads when my autonomous cars are willing to take just a little bit longer. Okay, so these are some of the equilibria that we can have when we have mixed autonomy. One question that might come up here is, well, why am I not talking about price of anarchy? This always comes up. So one thing to notice is that even if we have one type of vehicle, price of anarchy here is unbounded. So price of anarchy is not going to be useful for us here. And the reason is, when you look at the price of anarchy work, most of price of anarchy work use polynomial relationships between latency and flow. Our relationship between latency and flow is based on this fundamental diagram of traffic, which is not even a function. Right? So when we have this particular function, price of anarchy is just going to become unbounded. But this particular fundamental diagram of traffic is actually a better way of modeling traffic, a more realistic way of modeling how traffic flow actually runs. Okay? All right, so let me go back to my question. So now I know how to characterize various equilibria. I have Nash equilibrium, I have best Nash equilibrium, robust best Nash equilibrium, I can have altruism. So I know what would happen in steady state to my traffic network. But remember, the question I was really interested in is, how am I going to route my autonomous cars? So now I know how these equilibria look like, but I have no idea how to route my autonomous cars to get to those equilibria. And that's a question that I would want to talk about. So I know what I would like to get to, but I don't know how to get to that. Okay? All right, so to do that, I'm going to define 2 things that we need here. This is a dynamic problem, so we need to define dynamics. Where does the dynamics come from? So the dynamics is going to come from our flow. So we have a traffic network, and we have flow on these roads. So we're going to define cells. So every road is going to be a combination of cells, where every cell takes one time step to traverse. And the dynamics is, how is the flow traversing on this traffic network? And the way we do this, the way we model the road dynamics, is based on three main values. So one is the capacity of cell I minus 1. So if I'm going from cell I minus 1 to cell I, and I'm looking at the flow of that, it depends on the capacity, which is the maximum outflow that can go from cell I minus 1 to cell I. It depends on the demand, which is how many cars do I actually have on cell I minus 1. It also depends on supply, which is how many cars can get to the downstream, how many cars do I have space for to get to cell I. Okay? And then the flow is just a minimum of these 3 values, which is a very nonlinear dynamics function here. Okay? So we have this very nonlinear dynamics function that represents our flow dynamics of our traffic network. The second thing we need is how do humans make decisions here? So what is the human choice model that we are using? So in this case, we are assuming that our humans are using this Boltzmann distribution model, which is actually commonly used in HRI too, where we are basically saying our humans are making decisions on their routes based on this U vector, which is a distribution of what route they're going to take, the fraction of how many vehicles are going to go in each one of the roads. And it's proportional to your previous decisions, because you're not going to change that much. And it's also going to be proportional to exponential of negative delay, because if the delay is large, then you're not going to take that route. Okay? So this is specifically the human choice model that we are using. So now that I have the dynamics of the roads and I have the human choice model, I can just write an optimization that tries to solve this dynamic routing problem. The optimization is, I want to minimize the total delay subject to these dynamics that I just defined and the human choice model. And the fact that my decision variables here is how I'm routing my autonomous cars. It's the UA vector, which basically tells what is the fraction of autonomous cars that is going inside each one of the routes. And it's a probability vector, so it's going to add up to 1. Okay? All right, so this problem has a continuous state space. And it's in the order of hundreds. The state space is in the order of hundreds dimensional. So it's actually quite large. So the way we try to address this problem is we try to use reinforcement learning algorithms to try to approximate the solution to this particular dynamic programming problem. Okay? So the way we look at it is we have this traffic network. We're going to add a queue to this traffic network because what if we have a suboptimal social planner? Or what if the demand is infeasible? Under that scenario, well, the car's got to go somewhere. So let's add a queue that the cars can queue up there. And then in addition to that, well, we have this network. We can get the number of cars in the network. We can get the number of cars in the queue. And we can also get accident information from this network. So we model accidents in this case. And the way we model them are as a stochastic events. So the idea is accidents can block a lane in each one of these cells. And they disappear after t times, where t comes from the Poisson process. Okay? All right, so I can get this information from my network. I can train a neural network that gives me a routing vector, and that routing vector can be fed back into my dynamic routing problem, and I can keep running this and training this, and I could see, well, how that runs. Okay? So let's see how that actually works. Okay, so 2 roads is easy, so I'm just going to jump to 3 roads. So for the case where I have 3 parallel roads, the top plot here shows the training loss, and the bottom plot shows the actual loss that you would get. So you can see that the training loss goes down. So the dotted line, the dotted straight line, is the equilibrium. And we can see that the solid line is converging to equilibrium, which is the result that we are getting from RL. But if I have only selfish users, like if I'm not planning for my autonomous cars and everyone is selfish, we end up in this other regime where it blows up and the system becomes unstable and the cars get adding on the queue. Okay? So in the case of 3 roads, in the case of 4 roads, this kind of looks like this, the blue plot. Again, we get close to the equilibrium that we are looking for. In the case of selfish roads, it explodes. And then you can see the training loss going down. Okay? And one thing you might be wondering is, if I had access to that equilibrium, well, what am I doing here? Well, as just to reiterate, the equilibrium is the steady state, right? That's the thing that I know I would like to get to, but I have no idea how to get to it from any initial state. But the RL here is actually trying to achieve to it from any initial state. And this is actually averaged out over 100 runs of initial states, and this is what we get. Okay? All right, so let's pick the 3-road case. So I'm going to consider the 3-road case. This is what we have seen already for the 3-road case. RL is converging. If I'm not using RL and everyone is selfish, this is going to blow up. What if we add accidents? OK, so let me add accidents. So if I'm adding accidents randomly to some of the intervals, again, the reinforcement learning algorithm allows us to converge to the equilibrium. But in the case of selfish users, it's going to blow up. And here are some videos of what we would see. So this is a 5-hour simulation. So this is 5 hours of cars driving on this road. The top part is selfish routing. So again, everyone is selfish. The bottom ones are for the case when we have reinforcement learning. This is the 3-road case. So we have road 1, road 2, road 3. These are different length roads. And then I'm actually showing the queue too. So the queue that we saw, which is at the beginning of the roads. And again, you can see that in the case of selfish routing, as time passes, the queue is just filling up. So the queue is blowing up. But in the case of RL routing, we are able to clear out the queue, and the system becomes stable. So this is basically a video of what I was just showing in the plots. OK, so just to summarize this part of the talk, the idea here that we are using is we're trying to leverage autonomous vehicles' routing decisions to influence the routing decisions of human-driven cars, so we can actually have a better equilibrium and reduce the congestion on roads and influence some of these societal scale objectives that we care about, like traffic. So, and then just to reiterate, this is work that we have done with Erdem and Daniel and Ramtin. If you're interested in any of these works, I can talk about them offline too. OK, so we talked about dynamic routing. We've talked about static routing. And in general, we've talked about influencing behaviors in these macro type models, like a traffic model. And I want to spend just the last 2 minutes talking about a few of these other directions that I think would be exciting to look at. So one question that you might be thinking about is, well, I've talked about this high-level, macro-level behavior of roads, but what is really happening at the vehicle level? And that's actually something that we have been looking at. This is work that I started when I was at Berkeley, and this work with Anka, Shankar, and Sanjit, where we looked at a game-theoretic way of interaction between autonomous cars and human-driven cars, where autonomous cars start nudging in front of human-driven cars to influence them and make them slow down. And we have this game-theoretic way where the autonomous car thinks about how to influence humans based on models of humans. And I think these sort of interactions become important. And one problem that we're currently thinking about is how could we use some of these local models and connect them to some of these macro ideas. So these are very micro models of interaction. How do these influencing behaviors can influence some of these macro level, traffic level behaviors that we're looking at? And in addition to driving, this comes up all the time in robotics too. So if you're looking at human-robot interaction, in human-robot interaction, we're very interested in influencing and interacting with humans. And to do that properly, you need to have good models of humans. And that is hard, right? Like building good models of humans in HRI is really difficult. So one effort that we have been working towards is how can we intelligently and actively learn models of humans with minimal data that we get from various sources? So what if I have data from demonstrations, from preferences, rankings, even like physical feedback? And how can I query people to get good data to build better models of humans? And then I can use those models in these influencing regimes and in these game theoretic ways of looking at interaction. And finally, another direction that I'm super excited about is human-robot teaming. So how do I scale this up when I have multiple humans and multiple robots and them interacting with each other? So a setup that the recent work that we are looking at is what if we have multiple humans coming together and they want to do a collaborative task like going to an island, let's say, together? Can we extract these relationships that exist between the humans, like a leader-follower relationship, and have this scalable way of looking at this relationship and allow a robot to have that knowledge and influence them, influence the whole team as opposed to one of them, and influence them and get them to do a different task, which is something that we're going to present at RSS this year. And I just want to briefly mention, like a minute, about some other directions that I think is interesting. So we've been looking at influencing, right? A robot influencing humans. The human is not just going to sit there, right? The human is not going to be like, OK, fine, I'm influenced. Right? The human is going to respond and try to influence the robot too. And we have this game that keeps going, right? You influencing humans, humans influencing you, and this can go forever until like we converge to some equilibria. And I really think this happens in driving a lot of times, right? Like the reason that people, let's say in Iran, drive very differently than people in the US or in Palo Alto, the reason is they just ended up in different equilibria, in different conventions, in different cultures, which is based on these interactions that they had. And I think it's interesting to look at mutual adaptation and how that comes up in various scenarios. So everyone who lives in the Bay Area has a favorite story of autonomous driving. So my favorite story of autonomous cars is seeing these cars getting stuck at intersections. So when I see them, what I do is I just go around them. So this is kind of crazy, because based on my 3 interactions with an autonomous car, I've decided to just go around them. Okay? So my behavior has adapted to these autonomous cars. I'm giving wrong data to autonomous car companies, which is kind of scary. But I think it's an important problem to think about. And we have started thinking about this in the setting of language, where we have 2 humans coming together and building conventions. So maybe the first time a person refers to an object, might refer to a picture, might refer to it as a man is playing with a frisbee in a field. But over time, you would reduce to just calling that a frisbee based on your interaction with the same speaker and listener. So we are thinking about how we can build speakers and listeners that adapt to each other and how that applies to HRI problems. So with that, I just want to thank the group and thank you guys.
Thank you. We have time for maybe one or quite quick question while we. Yes.
How sensitive is your method to the model you used in the traffic situation for the humans?
So for the traffic stuff, this could work with different types of models. So so the RL actually would work with any types of models. You could put your favorite traffic model there, and that would work. With Equilibria, we are using ideas from the fundamental diagram of traffic to come up with these properties and use them to actually like characterize computing the Equilibria. But it's actually not very sensitive to that.
Kyriakos.
Thank you for the talk. I have a question regarding the multiple equilibria and how you quantify robustness and all these things. Because, I mean, game theoretic equilibria are already robust. So what do you mean by robustness and what do you mean by bestness?
OK, so when we have Nash equilibria, like these cars might end up in a situation where they don't necessarily deviate, but you would have a specific delay for that. So best Nash equilibrium is when you have the minimal delay. And even when you have minimal delay, when you have mixed autonomy, you might have multiple situations. You might have situations where you have human-driven cars on one road or another road. Both of them are going to be best Nash equilibria with minimal delay. Robustness is basically tries to differentiate between them. And the idea is if I can add more cars, which one of these two are going to stay at the same equilibria? And that's how we are defining robustness in this case.
Because already Nash has provided you some robustness. So what do you mean by this extra robustness?
So Nash
have
basically...
you quantified that extra robustness in a way?
So this is order of equilibrium, right? So this is basically you get to, so this is the extra robustness. The way we are defining it is you can handle unexpected traffic. Nash is basically telling you you're not going to deviate, which are two different things, right? You're not going to deviate from a road versus I add more cars, what will happen? Two different definitions. So that's what our definition is for robustness.
I think we have to move on to the next speaker, so let's thank Dorsa again.